17 miles beneath the Earth, a machine colder than the void of space is smashing protons together at nearly the speed of light. Every second, billions of collisions create conditions not seen since the dawn of time, unveiling mysteries that could shatter our understanding of reality. Are you ready to see what lies beyond the edge of known physics? If you're fascinated by the secrets of the universe and want to follow the discoveries that could change everything, make sure to subscribe and turn on notifications. The next breakthrough could happen at any moment, and you won't want to miss it. Deep beneath the borderlands of Switzerland and France, a colossal machine operates in conditions more extreme than the emptiest reaches of space. Here, in a tunnel stretching for 17 miles, particles are propelled to velocities just shy of the speed of light, colliding billions of times every second. The resulting temperatures at the collision points soar far beyond anything found in the natural universe. Amidst this orchestrated chaos, scientists are uncovering subtle inconsistencies, tiny deviations in the mathematical frameworks that describe our reality. Some of these irregularities hint at unknown forces, while others suggest the existence of particles that defy current understanding. Imagine a ring so vast it loops beneath two nations, carved through layers of earth and stone, lying 100 meters below the surface. This is the Large Hadron Collider, the most ambitious scientific instrument ever constructed by humanity. Its mission is to probe the most fundamental question: what is the true nature of everything around us? Above this subterranean marvel, life continues as usual. People go about their routines, unaware that, directly beneath their feet, streams of particles are racing through a vacuum at speeds that would allow them to circle the globe 7 times in a single second. The collider itself resembles something out of a futuristic vision. The tunnel is lined with thousands of superconducting magnets, each encased in cables finer than a strand of hair yet stronger than steel. These magnets serve a single purpose: to bend the paths of the particles, keeping them from flying off into the surrounding rock. The engineering required to achieve this is almost beyond belief. To function, the magnets must be cooled to an astonishing 2071 degrees C, colder than the void between galaxies. Maintaining this temperature demands 96 tons of liquid helium, circulating constantly. Even a slight increase in temperature could cause the entire system to fail. Within this frigid ring, 2 beams of protons are accelerated in opposite directions. Each beam contains billions of particles, circling the ring over 11,000 times every second, gaining energy with each pass. At these speeds, the effects of Einstein's theory of relativity become significant. Time slows down for the protons compared to the world outside. This isn't just theory, it's been measured and confirmed. When the beams are finally brought together, the protons collide with a combined energy of 13 trillion electron volts. The impact zone is smaller than an atom, and the violence of the collision is unmatched by anything found in nature on Earth. In these fleeting moments, energy is converted into matter. Particles that haven't existed since the universe's earliest moments are briefly brought into existence. This is the essence of what happens at CERN, recreating the conditions that prevailed a fraction of a second after the Big Bang. 4 enormous detectors, each the size of a cathedral, surround the collision points. They record every particle, every burst of energy, every clue that might reveal the universe's hidden structure. Scientists from more than 70 countries work here, united by a shared drive to uncover the building blocks of reality. They devote years, even decades, to the pursuit of answers that could fundamentally alter our understanding of existence. The collider has already revealed phenomena that were once thought impossible. But its most surprising discoveries have forced physicists to reconsider the very equations they once trusted. The journey of a proton in the collider begins in the most unassuming way as hydrogen gas, drawn from a small red canister. Hydrogen, the simplest and most abundant element in the universe, is transformed through a series of steps. First, the electrons are stripped away, leaving only the positively charged protons. These protons are then accelerated in stages, much like runners in a relay race, each stage handing off to the next, faster one. The ultimate speed limit is the speed of light, a boundary that nothing with mass can cross. Yet, the protons come incredibly close, reaching 99.99999% of light speed by the time they enter the main ring. At this velocity, the difference between their speed and the speed of light is almost imperceptible. To put it in perspective, a proton completes over 11,000 laps of the 17-mile ring every second. If you could somehow observe it, you wouldn't see a distinct object, but rather a blur, a presence defined more by mathematics than by physical form. At such extreme speeds, the proton's mass increases dramatically, as dictated by relativity. A stationary proton is almost weightless, but at near light speed, it becomes thousands of times heavier. This has been confirmed by every measurement taken at CERN. But the strangeness doesn't end there. Time itself is distorted. From the proton's perspective, its journey around the ring is almost instantaneous. To an outside observer, the proton appears to age more slowly, caught in a kind of temporal limbo. This is not speculation, it's a measurable effect, a direct consequence of approaching the universe's ultimate speed limit. The energy required to sustain these speeds is immense. The collider consumes as much electricity as a small city. The magnets must constantly counteract the natural tendency of the particles to fly apart. Every millisecond is a contest between human ingenuity and the fundamental forces of nature. When the moment of collision arrives, the beams are focused to a width finer than a human hair. The timing must be flawless. Even the slightest misalignment means nothing happens. But when the protons do collide, the energy released is staggering. For a brief instant, the temperature at the collision point reaches several trillion degrees, hotter than the core of any star, hotter than anything else in the universe today. In this searing heat, matter dissolves into its most basic components. What emerges from this chaos has already rewritten the textbooks once, and many believe it will do so again. For half a century, physicists faced a puzzle their equations couldn't solve. The mathematics predicted that fundamental particles should have no mass at all, while yet everything around us clearly has mass. Something was missing from the equations. In the 1960s, a group of theorists proposed a solution, an invisible field permeating all of space. As particles move through this field, they experience resistance, which we perceive as mass. This field, if it existed, would also produce a particle, a quantum of the field itself. They called this particle the Higgs boson, but finding it was a monumental challenge. The Higgs boson is unstable, existing for less than a trillionth of a second before decaying into other particles. It can't be captured or observed directly, only the traces it leaves behind can be detected. For decades, scientists searched in vain, building ever more powerful machines and analyzing countless collisions. Some began to doubt whether the particle was real, or if the theory itself was flawed. Then, on a summer day in 2012, everything changed. In a packed auditorium at CERN, researchers announced that they had found compelling evidence for the Higgs boson. Two separate detectors, using different methods, had both observed its signature. The statistical certainty was overwhelming. The room erupted in celebration. Peter Higgs, The physicist who had first proposed the idea nearly 50 years earlier was present, moved to tears by the confirmation of his life's work. The discovery was a triumph, but it also raised new questions. The Higgs boson's mass, about 125 billion electron volts, is peculiar. It falls within a range that suggests the universe might not be as stable as we once thought. The measured mass of the Higgs boson is not just a number, it carries profound implications for the fate of the universe. The value sits in a narrow window that, according to theoretical calculations, could mean the very fabric of reality is precariously balanced. The vacuum of space, which we think of as empty, might actually be in a temporary, unstable state. If the underlying energy of the vacuum were to shift, even by a minuscule amount, it could trigger a catastrophic transformation, an event physicists call vacuum decay. In such a scenario, a bubble of true vacuum would form somewhere in the universe, expanding at the speed of light and altering the laws of physics within it. Everything as we know it would cease to exist, replaced by a new reality with different rules. This is not just idle speculation. The mathematics of quantum field theory allows for such possibilities, though the timescales involved are likely far longer than the current age of the universe. Still, the mere fact that our universe might be teetering on the edge of stability is unsettling. The only way to know for sure is to measure the properties of the Higgs boson with ever-increasing precision, especially how it interacts with itself, a property known as self-coupling. So far, experiments at CERN have narrowed down the possible values, but the uncertainty remains large. The next generation of experiments aims to tighten these constraints, seeking to determine whether our universe is truly stable or merely balanced on a cosmic knife edge. The Higgs boson is unique among fundamental particles. While all particles interact with others, electrons repel each other, quarks bind together, photons mediate electromagnetic forces. The Higgs is predicted to interact with itself in a way no other particle does. The equations suggest that 3 or even 4 Higgs bosons can meet at a single point, a phenomenon known as self-interaction. Detecting this is extraordinarily difficult. Finding a single Higgs boson took decades and billions of collisions. Observing 2 or more at once is 1,000 times harder, but scientists are determined. The reason is simple. The self-coupling of the Higgs determines the shape of the energy landscape in which the universe sits. If the landscape is deep and stable, the universe is safe. If it is shallow, with a hidden drop-off, the universe could one day tumble into a new state. Quantum mechanics allows for the possibility that, through a random fluctuation, the Higgs field could cross this barrier, initiating vacuum decay. Inside the resulting bubble, the constants of nature would change. Atoms' forces, even the speed of light could be different. The bubble would expand at light speed, erasing everything in its path. There would be no warning, no escape. One moment, reality would exist, the next it would be gone. While this is a theoretical possibility, there is no evidence it will happen anytime soon. The calculations suggest the universe is likely safe for trillions of years, but only more precise measurements can provide certainty. To maintain the conditions necessary for these experiments, the Large Hadron Collider must operate at temperatures colder than the emptiest regions of space. The natural temperature between galaxies, where no stars shine, is about 27 degrees C, just above absolute zero. The collider's superconducting magnets, however, must be kept even colder, down to 71 degrees C. Achieving this requires a complex system that circulates 96 tons of liquid helium throughout the machine. Helium is the only element that remains liquid at such low temperatures. Everything else would freeze solid. The system must be meticulously maintained. Even a tiny leak or a small rise in temperature can cause catastrophic failures. Such failures have happened before. In 2008, during the collider's initial startup, a faulty electrical connection caused a spark, which rapidly heated a section of the machine. The sudden heat vaporized helium, creating a pressure wave that damaged over 50 magnets and tore vacuum pipes from their supports. Repairs took more than a year and cost millions. The collider, despite its immense size, is surprisingly delicate. Even small animals have caused shutdowns, a bird dropping a piece of bread onto an outdoor power unit, or a weasel chewing through a cable, have both brought the machine to a halt. Engineers have learned to expect the unexpected, but when everything works, the results are extraordinary. At these ultra-cold temperatures, the magnets become superconducting, losing all electrical resistance. Electricity flows through them without generating heat, allowing for the creation of magnetic fields strong enough to bend particles moving at nearly the speed of light. In a normal wire, resistance would generate heat and waste energy, but in a superconductor, the current can circulate indefinitely without loss. This is what makes the collider possible. The main ring contains over 1,000 dipole magnets, each nearly 15 meters long and weighing 35 tons. The precision required to align them is astonishing, fractions of a millimeter matter. If a single magnet fails, the particle beam can veer off course, slamming into the tunnel wall with the energy of a speeding train. To prevent disaster, the collider is equipped with emergency systems that can divert the beam into a graphite block within milliseconds. The margin for error is razor thin. Everything must work in perfect harmony. The cold must be maintained. The magnets must function. The beams must stay aligned. When all these conditions are met, the collider becomes a kind of time machine, recreating the conditions of the early universe. In 2023, the collider was used to investigate one of the strangest mysteries in physics: antimatter. Every particle has an opposite, an antimatter counterpart with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other, converting their mass into pure energy. This process has been observed countless times and is a cornerstone of modern physics. Yet, a fundamental question remained: does antimatter respond to gravity in the same way as ordinary matter? According to Einstein's theory of gravity, all objects should fall at the same rate, regardless of their composition. But until recently, no one had ever tested this directly with antimatter. The challenge is that antimatter is incredibly difficult to handle. The moment it touches ordinary matter, both are destroyed. You can't simply drop antimatter and watch what happens. To solve this, CERN developed a special experiment that creates neutral anti-hydrogen atoms, combinations of antiprotons and positrons. These anti-atoms are suspended in a magnetic trap isolated from contact with normal matter. In 2023, researchers gradually weakened the magnetic field, allowing the anti-hydrogen atoms to escape. Detectors recorded where each atom annihilated. The results were clear: antimatter falls down, just like matter. Gravity treats both the same. This finding, while confirming expectations, deepens the mystery of why the universe is made almost entirely of matter. The Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other completely. Yet, for reasons still unknown, a tiny excess of matter survived, forming everything we see today. The experiment ruled out gravity as the cause of this imbalance, but the search for answers continues. While some researchers at CERN were busy unraveling the mysteries of antimatter, others were focused on a different anomaly, one that threatened to upend the very foundations of particle physics. This puzzle centered on a particle called the muon, a heavier cousin of the electron. Muons are similar to electrons in almost every way, except for their mass, which is about 200 times greater. They carry the same negative charge and respond to the same forces, so, in theory, they should behave in ways that are well understood and precisely predicted by the standard model of particle physics. However, when scientists measured how muons spin in a magnetic field, they noticed something odd. Every particle with a charge and spin acts like a tiny magnet. When placed in an external magnetic field, it wobbles, much like a spinning top that slowly precesses. The rate of this wobble can be calculated with extraordinary precision using quantum mechanics. The standard model predicts this value to many decimal places. But in the late 1990s, an experiment at Brookhaven National Laboratory in the United States found that the muon's wobble was slightly faster than the theory predicted. The difference was minuscule, but it was there, a hint that something might be missing from our understanding. Physicists refer to this measurement as G-2, where G is the gyromagnetic ratio. According to basic quantum theory, this value should be exactly 2, but quantum corrections nudge it slightly higher. The Brookhaven experiment suggested that these corrections were larger than expected, possibly due to unknown particles or forces influencing the muon. The result was intriguing but not definitive. The statistical significance hovered around 3 to 4 sigma, meaning there was still a small chance the discrepancy was just a fluke. To resolve the issue, a new experiment was built at Fermilab, using the same massive magnet from Brookhaven, which had to be transported across the country on a specially designed barge. Years of preparation followed, and in 2021, Fermilab released its first results. The anomaly persisted, the muon still wobbled more than the standard model predicted. But as the experimental precision improved, so did the theoretical calculations. Determining the muon's wobble requires accounting for every possible interaction it could have, including contributions from quarks, gluons, photons, and even more exotic possibilities. Some calculations rely on supercomputers running for months, while others use data from particle colliders to constrain the inputs. Different methods of calculation began to yield slightly different answers. One approach, using data from electron-positron collisions, supported the anomaly. Another, using a technique called lattice quantum chromodynamics, suggested the standard model might actually be correct. The two methods disagreed, shifting the mystery from the experiment to the theory itself. In June 2025, after 6 years of data collection, Fermilab released its final results. The experimental measurement now closely matched the revised theoretical prediction, and the anomaly that had haunted physics for a quarter-century faded, though it did not disappear entirely. Some tension remains between different calculation methods, and some physicists still suspect that new physics could be hiding in the numbers. For now, though, the standard model has survived another test. But as the muon mystery cooled, another crisis was brewing. This time, it involved the W boson, a particle that mediates the weak nuclear force, the force responsible for certain types of radioactive decay. The mass of the W boson is one of the most precisely predicted values in all of physics. The standard model says it should weigh about 357 million electron volts, a value derived from measurements of other particles and plugged into a web of interconnected equations. If any one number is off, the whole structure wobbles. In 2022, the CDF experiment at Fermilab announced a new measurement of the W boson's mass: 433 million electron volts. This was 76 million electron volts higher than the standard model prediction, a difference so significant that the chance of it being a statistical fluke was less than 1 in a trillion. If correct, This result would mean the standard model was broken. Physicists scrambled to interpret the finding. Some proposed new particles that had escaped detection, others speculated about unknown forces, or even extra dimensions. But there was a problem: other experiments did not agree. Measurements from CERN and earlier experiments at Fermilab, as well as from the Large Hadron Collider, all gave values much closer to the standard model prediction. The CDF result stood alone. Measuring the W boson's mass is extraordinarily difficult. The particle decays almost instantly into a muon and a neutrino. While muons can be tracked with high precision, neutrinos pass through detectors without interacting, so their properties must be inferred from what is missing in the collision. This requires a perfect understanding of the detector's response, every magnetic field, every material interaction, every calibration. Even small systematic errors can shift the final result. For 2 years, the physics community waited for clarification. Then, in September 2024, the CMS experiment at CERN released its own measurement, using 300 million collision events and the most advanced analysis techniques ever applied. Their result: 360 million electron volts, almost exactly what the standard model predicted. The CDF anomaly did not replicate. The crisis seemed to be over, but questions lingered. Why did CDF get such a different answer? Their methods have not been shown to contain obvious errors. Some physicists suspect undiscovered systematic effects, while others wonder if the disagreement hints at something deeper. For now, the standard model remains intact, but the episode is a reminder that even the most established theories can be challenged by new data. Meanwhile, in the aftermath of these high-profile measurements, scientists at the Large Hadron Collider were making discoveries of a different kind. In the debris of particle collisions, they found evidence for particles that, according to the old rules, should not exist at all. The building blocks of matter, quarks, come in 6 types or flavors: up, down, charm, strange, top, and bottom. Normally, quarks combine in simple patterns. 3 quarks make a baryon, like the protons and neutrons in your body. A quark and an antiquark make a meson. For decades, these were the only combinations observed, though theory allowed for more complex arrangements. The LHCb detector at CERN specializes in studying heavy quarks, particularly bottom and charm quarks. These particles are short-lived, traveling only a tiny distance before decaying, but their tracks can be reconstructed with remarkable precision. By analyzing these tracks, physicists began to find signals that did not match any known particle. In 2015, HCB announced the first confirmed pentaquark, a particle made of 5 quarks bound together. It existed for only an instant, but the signal was unmistakable. Then came the tetraquarks. In 2020, a particle made of 4 charm quarks was discovered, a configuration never seen before. These findings changed how physicists think about the strong force which binds quarks together. The discoveries accelerated. In 2022, 3 new exotic particles were reported in a single announcement: a pentaquark containing a strange quark, and 2 tetraquarks with unusual electric charges. The statistical significance of these findings was overwhelming. These were not random fluctuations, they were real, previously unknown forms of matter. The exact nature of these exotic particles is still debated. Some models suggest the quarks are tightly bound into a single object, while others propose they are more like molecules, 2 ordinary hadrons loosely held together. Understanding these states helps physicists probe the strong force and the conditions that existed in the early universe. The growing list of exotic particles discovered at the Large Hadron Collider has expanded what physicists call the particle zoo. More than 60 new hadrons, particles made of quarks, have been identified, many of which do not fit the simple patterns that dominated particle physics for decades. These discoveries are not just curiosities. They provide crucial insights into the strong nuclear force, one of the four fundamental forces of nature. The strong force is what binds quarks together inside protons and neutrons, and it is responsible for holding the nuclei of atoms together. By studying how quarks combine in these unusual ways, scientists are learning more about the rules that govern the most powerful force in the universe. Among the most intriguing phenomena observed at the LHC is quantum entanglement at unprecedented energy scales. Quantum entanglement is a phenomenon where two or more particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein once called it, has been confirmed in countless experiments with photons, electrons, and atoms. However, these experiments were always conducted at relatively low energies, in controlled laboratory settings. That changed in 2023, when the ADLAS collaboration at CERN announced the detection of quantum entanglement between top quarks, the heaviest fundamental particles known. Top quarks are produced only in the most energetic collisions and decay almost immediately, in less than a trillionth of a second. There is no time for them to interact in the usual sense, so their quantum properties must be inferred from the patterns left by their decay products. By carefully measuring the angles and correlations between these products, physicists were able to demonstrate that the top quarks were indeed entangled. The result was confirmed by the CMS collaboration, which extended the analysis to pairs of quarks moving at high relative speeds, where even the speed of light would not allow for classical communication between them. Yet, entanglement persisted. This breakthrough is more than a technical achievement. It shows that quantum mechanics, with all its counterintuitive predictions, holds true even in the most violent environments humans can create. The techniques developed to detect entanglement at the LHC are now being used to search for new physics. Any deviation from the expected quantum correlations could signal the presence of unknown particles or forces. So far, the Standard Model continues to pass these tests, but the search is far from over. While confirming the predictions of quantum mechanics is important, the ultimate goal at CERN is to find what lies beyond the Standard Model. One of the biggest mysteries in physics is the imbalance between matter and antimatter. According to the laws of physics as we understand them, the Big Bang should have produced equal amounts of both. When matter and antimatter meet, they annihilate each other, leaving only energy behind. Yet, the universe we observe is made almost entirely of matter. The amount of antimatter is vanishingly small. This asymmetry is the reason galaxies, stars, planets, and people exist. Physicists believe the answer lies in a phenomenon called CP violation. CP stands for charge conjugation and parity. Charge conjugation swaps particles for their antiparticles, while parity flips the spatial coordinates, like looking in a mirror. If the laws of physics were perfectly symmetric, flipping both charge and parity should make no difference. But experiments have shown that certain particles decay slightly differently than their antiparticles, violating this symmetry. The effect is small but real, and it is encoded in the mathematics of quark mixing within the Standard Model. The question is whether the known amount of CP violation is enough to explain the matter-antimatter imbalance. Most calculations suggest it is not. The effect is too weak by many orders of magnitude. Something else must be at work. The LHCb experiment at CERN specializes in studying CP violation, particularly in particles containing bottom and charm quarks. In 2025, The collaboration announced a significant result: the first observation of CP violation in baryons, particles made of three quarks like protons and neutrons. Previously, CP violation had only been confirmed in mesons, which are made of two quarks. By comparing the decay rates of certain baryons and their antimatter counterparts, physicists detected a small but unmistakable asymmetry. This discovery does not solve the mystery, but it adds a new piece to the puzzle. The observed CP violation in baryons is still too small to account for the dominance of matter in the universe. But it confirms that the effect is more widespread than previously thought. Each new measurement narrows the possibilities, pushing the search for new physics into ever more subtle territory. If the standard model cannot explain the asymmetry, then new particles, forces or interactions must exist, hidden from every experiment so far. But the visible matter studied at the LHC is only a tiny fraction of what makes up the universe. All the protons, neutrons, electrons, and even the Higgs bosons add up to just about 5% of the total cosmic inventory. The rest is invisible. About 27% is dark matter, an unknown substance that does not emit, absorb, or reflect light, and interacts with ordinary matter only through gravity. The remaining 68% is dark energy, a mysterious force that is causing the expansion of the universe to accelerate. The existence of dark matter is supported by multiple lines of evidence. In the 1970s, astronomer Vera Rubin measured the rotation speeds of stars in galaxies, and found that the outer stars were moving much faster than could be explained by the visible mass alone. The only explanation was the presence of unseen mass exerting a gravitational pull. Other observations, such as gravitational lensing and the patterns in the cosmic microwave background, all point to the same conclusion. Most of the universe's mass is dark. Physicists have proposed many candidates for dark matter. For decades, the leading theory was that dark matter consists of weakly interacting massive particles, or YMPs. These hypothetical particles would have been produced in the early universe, and would rarely interact with ordinary matter, making them difficult to detect. The LHC has searched for YMPs by looking for events where energy seems to vanish, possibly carried away by an invisible particle. So far, no such events have been found, but the search continues. Other possibilities remain. Axions, hypothetical light particles originally proposed to solve a different problem in the strong force, could also make up dark matter. Sterile neutrinos, which do not interact via the weak force, are another candidate. Some theories even suggest that dark matter could be made of primordial black holes formed in the early universe. Each possibility is being explored through a combination of collider experiments, underground detectors, and astronomical observations. Dark energy is even more mysterious. Discovered in 1998 through observations of distant supernovae, it appears to be a property of space itself, pushing galaxies apart at an ever-increasing rate. The nature of dark energy is unknown, and it cannot be studied directly at the LHC, as the energies involved are far too low. But if dark matter is made of particles, there is a chance that the LHC could produce them. Every collision is a chance to glimpse something new, something invisible, something that could change our understanding of the cosmos. While the search for dark matter continues, the Large Hadron Collider has also allowed scientists to recreate a state of matter that last existed just after the birth of the universe. For a brief period each year, the collider switches from accelerating protons to smashing together heavy ions, specifically, lead nuclei. Each lead nucleus contains 82 protons and 126 neutrons, stripped of their electrons and accelerated to nearly the speed of light. When these massive nuclei collide, the energy density is so extreme that the protons and neutrons themselves melt, releasing the quarks and gluons that are usually confined within them. This creates a new form of matter known as quark-gluon plasma. Quark-gluon plasma is not like any ordinary substance. It is a fluid made not of atoms or molecules, but of the fundamental building blocks of matter, quarks and gluons, moving freely in a hot, dense soup. This plasma is the hottest material ever created in a laboratory, reaching temperatures of several trillion degrees, far hotter than the core of any star. At these temperatures, the strong force that normally binds quarks together weakens, just enough to let them roam independently, if only for a fleeting moment. The LIC experiment at CERN was designed specifically to study this exotic state of matter. Unlike the other detectors, which focus on rare events and new particles, LIC is built to analyze the collective behavior of thousands of particles produced in each heavy-ion collision. What scientists found was surprising. The quark-gluon plasma behaves almost like a perfect liquid, with extremely low viscosity. Instead of acting like a chaotic gas, as many theorists had predicted, the plasma flows smoothly, with ripples and waves that reflect the geometry of the original collision. This discovery challenged previous assumptions and opened new avenues for understanding the early universe. Studying quark-gluon plasma is like peering back in time to the first microsecond after the Big Bang. In those earliest moments, the entire universe was filled with this plasma. As the universe expanded and cooled, the quarks and gluons condensed into protons and neutrons, which later formed the first atoms. Every element in your body, carbon, oxygen, iron, passed through this primordial phase. By recreating these conditions at the LHC, scientists can directly study the properties of matter as it existed at the dawn of time. The experiments have also revealed unexpected features. For example, the plasma produces more particles containing strange quarks than simple models predicted. This suggests that the environment inside the plasma favors the creation of certain types of quarks, providing new insights into how the strong force operates under extreme conditions. There are also hints that even in smaller collisions, such as those between protons, tiny droplets of quark-gluon plasma may form and evaporate almost instantly. The boundary between ordinary matter and this exotic state is less clear-cut than once thought. Each year, as more data is collected, the picture becomes clearer. The study of quark-gluon plasma not only helps explain the early universe, but also informs our understanding of neutron stars, where similar conditions may exist. The discoveries made at the LHC are reshaping our knowledge of how matter behaves at the most fundamental level. But not all events at the collider are common. Some are so rare that they require years of data collection to observe. One such event is the decay of the Higgs boson into a pair of muons. The Higgs can decay in many ways, but the decay into muons happens only about 2 times in every 10,000 decays. The signal is buried under a mountain of background noise, as other processes produce muon pairs far more frequently. Extracting the Higgs signal required new analysis techniques, including machine learning algorithms trained to recognize the subtle patterns left by Higgs decays. In 2020, the ADAS experiment announced the first evidence for this rare decay, with a statistical significance strong enough to suggest a real effect but not yet definitive. The CMS experiment found similar results. By 2024, with more data and improved analysis, the combined results reached the threshold for discovery. This measurement is important because it tests how the Higgs boson interacts with the second generation of fundamental particles. If the observed rate of decay into muons differed from the standard model prediction, it would be a sign of new physics. So far, the results match expectations, but the precision continues to improve with each new dataset. A similar story is unfolding with another rare decay, the Higgs transforming into a Z boson and a photon. This process is even less common, occurring in less than 1 in 1,000 decays. Evidence for this channel appeared in 2022, but full confirmation will require more data. These rare decays are important because they probe the standard model at its most delicate points, testing the quantum loops where virtual particles flicker in and out of existence. Any deviation from the predicted rates could reveal the influence of particles too heavy to produce directly. The sheer volume of data collected at the LHC is staggering. Since it began operating, the collider has recorded hundreds of trillions of collisions. Each collision is a snapshot of the universe as it was in the first instant after the Big Bang. Most of the data has been analyzed, but the process never truly ends. New analysis techniques, including advanced machine learning, continue to find patterns that were previously missed. Improved calibrations and theoretical advances can change the interpretation of old measurements. Sometimes, discoveries are made not by collecting new data, but by looking at existing data in a new way. CERN maintains vast archives of collision data, ensuring that future generations of physicists can reanalyze it with better tools. Portions of the data have even been released to the public, allowing students and independent researchers to search for new phenomena. The potential for discovery is enormous. A particle that decays in an unexpected way, or a subtle correlation between variables, might be hiding in the data, waiting for someone to notice. The LHC is not just a machine for smashing particles, it is a time machine, a microscope, and a treasure trove of information about the universe's most fundamental secrets. As the collider continues to operate and upgrades increase its capabilities, the chances of finding something truly revolutionary grow. Whether it is a new particle, a deviation from the standard model, or a glimpse of dark matter, the next breakthrough could be hiding in the next collision, or in data already collected, waiting for the right question to be asked. The future of the Large Hadron Collider is set to become even more ambitious. In 2029, a major upgrade known as the High Luminosity LHC will transform the machine, increasing the number of collisions by a factor of 5 to 7. Where the collider currently delivers about 1 billion collisions per second at full intensity, the upgraded version will reach up to 7 billion. This leap in collision rate means that rare events, such as the production of Higgs bosons, or the appearance of exotic particles, will become more accessible. Precision measurements that are currently limited by the amount of data will improve dramatically, opening new windows into the unknown. Achieving this upgrade is no small feat. The technology required is cutting-edge. Magnets near the collision points must be redesigned to focus the beams more tightly, and the beams themselves will be restructured into denser bunches. The detectors, already marvels of engineering, must be rebuilt to handle 10 times more simultaneous collisions without being overwhelmed. Radiation damage is a major concern. The increased collision rate means that components that once lasted for years will now degrade much faster. Entire sections of the detectors are being replaced with materials that can withstand the harsher environment. Timing is another challenge. With so many collisions happening at once, the detectors must be able to distinguish which particles came from which collision. New timing layers are being installed, capable of measuring the arrival of particles to within a few tens of trillionths of a second. The data rate will explode. Currently, the system records about 1,000 collision events per second, selected from the billion that occur. The upgraded collider will require smarter triggers, systems that can identify interesting events in real time, filtering the data before it is even recorded. Machine learning algorithms will play a crucial role, running at lightning speed to ensure that no important event is missed. The physics program for the high luminosity LHC is ambitious. One of the main goals is to measure the Higgs boson's self-coupling with enough precision to test the shape of the Higgs potential, the energy landscape that determines the stability of the universe. Another is to observe the rare decay of the Higgs to muon pairs with definitive significance. The search for supersymmetric particles, especially in scenarios that are difficult to probe with current analyses, will intensify. Every component of the machine and its detectors is being improved, involving thousands of engineers and scientists from around the world. The cost is measured in billions of dollars, and the timeline stretches over a decade, but the potential rewards are immense. If new physics exists just beyond our current reach, the upgraded collider will be the tool to find it. While the LHC pushes the boundaries of what is possible with protons, physicists are also exploring other ways to reach higher energies. Protons are complex objects, made of quarks and gluons, each carrying only a fraction of the total energy. When protons collide, only some of that energy is available to create new particles, the rest is lost in a spray of debris. Electrons, by contrast, are fundamental particles, but they are light and lose energy quickly when bent in a circle, limiting how fast they can be accelerated in a ring of reasonable size. Muons offer a promising alternative. A muon is 200 times heavier than an electron, so it radiates far less energy when bent, allowing it to reach higher energies in a smaller ring. Unlike protons, muons are fundamental, so all their energy is available for creating new particles. A muon collider could achieve collision energies of 10 trillion electron volts in a ring only 10 kilometers around, nearly as much as the LHC delivers in a ring 3 times larger. The challenge is that muons are unstable, decaying in about 2 microseconds at rest. Even at high speeds, where time dilation extends their lifetime, they survive only long enough to circle a small ring a few thousand times. That is just enough for collisions to occur. Building a muon collider is a formidable technical challenge. Engineers must produce muons, cool them into a tight beam, accelerate them to high energy, and collide them before they decay, all in a fraction of a second. The technology is still in development, but progress is being made. Laboratories in the United States, Europe, and Japan are testing components, demonstrating cooling techniques, and designing acceleration schemes. If successful, a muon collider could operate by the 2040s, offering a new path to discoveries that are out of reach for current machines. The physics potential of a muon collider is extraordinary. It would allow for the direct production of Higgs bosons in the collision. Thanks to the Moon's strong coupling to the Higgs field, it would enable searches for new particles at energies far beyond the LHC, and it could measure the Higgs self-coupling with greater accuracy than any hadron collider. The muon collider represents a different philosophy, smaller, potentially less expensive, but technically more challenging and possibly more rewarding. Which path the field takes will depend on funding, technological progress, and scientific priorities. No matter which machines are built, the drive to explore higher energies and greater precision will continue. The questions are too important, and the mysteries too deep, for humanity to stop searching. Somewhere, a new machine will probe energies higher than the LHC, and that machine will either confirm our current understanding or shatter it completely. At the heart of all these efforts is a profound question: why is there something rather than nothing? The Big Bang created space, time, matter, and energy, but the reason for its occurrence remains a mystery. Physics can describe the evolution of the universe from a fraction of a second, after the Big Bang onward, but it cannot explain why the initial conditions were what they were, or why the laws of physics take the form they do. The Standard Model takes the existence of certain particles and forces as given, but it does not explain why those particles and forces exist, or why they have the properties they do. Some physicists speculate that our universe is just one of many, each with its own laws, a multiverse. In this view, we observe the laws we do, because they allow for the existence of observers. Other universes with different laws might exist, but with no one to ask questions. This idea is controversial and unsatisfying to many, as it replaces one mystery with an infinite number of mysteries. Others hope for a deeper theory, a mathematical structure so compelling that it uniquely determines the laws of nature. So far, no such theory has been found. CERN cannot answer these ultimate questions directly, but every measurement, every discovery, and every confirmation of the Standard Model helps to narrow the range of possibilities. The physicists smashing particles together are not just searching for new particles, they are mapping the boundaries of human knowledge. Somewhere beyond those boundaries lies the answer, or perhaps the realization that the universe simply is, requiring no further justification. Either possibility is profound. Every day at CERN, teams of scientists and engineers monitor the collider's performance, scrutinizing data as it streams in from the detectors. The control center operates around the clock, with shifts of experts watching over thousands of parameters, beam positions, magnet currents, vacuum pressures, and cryogenic temperatures. Most nights are uneventful, with the machine humming along, the beams circulating in opposite directions, and billions of protons making their 11,000 laps per second. But the unexpected is always possible. In the past, a weasel gnawing through a cable, or a bird dropping a piece of bread onto outdoor equipment, has brought the world's largest scientific instrument to a halt. When something goes wrong, the response is immediate. The beam is safely dumped, the magnets ramp down, and the cause is investigated and repaired. Every hour of downtime is an hour of lost data, a missed opportunity for discovery. The process of collecting and analyzing data at the LHC is a marvel in itself. Each collision generates about a megabyte of information. And with hundreds of millions of collisions every second, it would be impossible to record everything. The data rate would overwhelm the world's storage capacity in a matter of hours. To manage this, the detectors use a sophisticated trigger system that makes split-second decisions about which events to keep and which to discard. The first level of triggers is hardware-based, designed for speed, and looks for high-energy particles or unusual patterns. Only about 1,000 events per second survive this initial filter. Software triggers then analyze these survivors in more detail, reconstructing particle tracks and calculating energies. Events that might contain rare particles or unexpected signatures are kept. The rest are discarded. This system is not without its risks. If the triggers are too narrowly focused on known physics, they might miss something truly new. To guard against this, some bandwidth is reserved for random sampling, saving a fraction of all events, regardless of their apparent significance. The trigger menus are constantly updated as new theoretical ideas emerge, and as old searches are completed. Artificial intelligence is playing an increasing role, with neural networks learning to identify anomalies without being told exactly what to look for. Still, the fundamental challenge remains. Most of what happens in the collider is lost forever, and the discoveries we make depend on the choices we make about what to keep. Once the data is recorded, it is distributed to a global network of computing centers known as the worldwide LHC computing grid. This network spans more than 40 countries and includes over 170 computing centers. The data flows from Geneva to laboratories around the world, where thousands of processors work in parallel to analyze it. The grid operates continuously, with physicists in different time zones taking over as others sleep. Machine learning has revolutionized the analysis process, allowing for the identification of rare events and subtle patterns that would have been impossible to find with traditional methods. The algorithms are constantly improving, and what was state of the art last year may already be obsolete. Behind every algorithm, though, is a human mind. Physicists design the analysis strategies, check the results, and interpret the findings. The grid amplifies human intelligence but does not replace it. Somewhere in the vast sea of data, patterns await discovery. If only the right questions are asked. CERN maintains archives of all the data collected, ensuring that future generations can reanalyze it with better tools. Portions of the data have even been released to the public, inviting students and independent researchers to join the search for new phenomena. The detectors themselves are engineering marvels. ATOAS, for example, is a structure the size of a 7-story building, weighing more than the Eiffel Tower, yet capable of measuring particles smaller than atoms with astonishing precision. Its layers of sensors track the paths of charged particles, measure their energies, and identify their types. The compact muon solenoid takes a different approach, using a powerful solenoid magnet to bend the paths of particles in a more compact volume. Both detectors were designed independently, by separate teams using different technologies and analysis methods. This redundancy is intentional. When both detectors see the same signal, it is almost certainly real. The discovery of the Higgs boson required confirmation from both ATLAS and CMS, and every major result at CERN follows this pattern. The detectors operate continuously when the beams are running, recording collision after collision, year after year. The sensors degrade from radiation, components fail and are replaced, but the machines keep working. They are cathedrals of science, built not for worship, but for understanding. Hidden within their silicon and steel may already be the clues to the next great discovery. Not all experiments at CERN are focused on the heaviest particles or the highest energies. Some are designed to search for the rarest decays. The LHCb experiment specializes in studying particles containing beauty quarks. These quarks are heavy and unstable, traveling only a tiny distance before decaying. But that distance is measurable and leaves a distinctive signature. LHCb is built as a forward spectrometer, optimized to catch particles that fly along the beamline, where beauty quarks tend to go. By measuring how often different decay modes occur, physicists can test the standard model with extreme precision. Tiny deviations from the expected rates could reveal the influence of new particles or forces. So far, LHCb has found no clear deviations, but the measurements are more precise than ever. The constraints on new physics are tighter, and whatever lies beyond the standard model must be subtle enough to have escaped detection so far. The same is true for strange quarks, which are lighter but still unstable. Their decays probe the weak force in complementary ways, and decades of experiments have built a consistent picture. The standard model describes flavor physics, the way quarks change type, with remarkable success, but it does not explain why the mixing parameters have the values they do. A deeper theory would predict these numbers, but for now, they are simply measured. The search for new physics continues on many fronts. Each experiment, each analysis, Each upgrade brings us closer to the edge of what is known. The LHC is not just a machine. It is a global collaboration, a testament to human curiosity and ingenuity. The next breakthrough could come from a rare decay, a subtle anomaly, or a pattern hidden in the data. Or it could come from a completely unexpected direction, forcing us to rethink everything we thought we understood about the universe. The story of the universe's earliest moments is written in the language of phase transitions. In the first trillionth of a second after the Big Bang, everything was different. All particles were massless, and the electromagnetic and weak nuclear forces were unified as a single force. The Higgs field, which today gives particles their mass, had not yet settled into its lowest energy state. Everything moved at the speed of light, and the universe was a seething, hot plasma of energy and potential. As the universe expanded and cooled, the Higgs field underwent a dramatic transformation. It rolled from the peak of its potential energy down into a valley, a process known as spontaneous symmetry breaking. This event, called the electroweak phase transition, split the unified force into the separate electromagnetic and weak forces we observe today. Particles that interacted with the Higgs field gained mass, while those that did not, like photons, remained massless. The details of this transition are crucial, as they set the stage for everything that followed. Physicists are intensely interested in whether this transition was smooth and gradual, like ice melting into water, or violent and abrupt, like water boiling into steam. If the transition was a gentle crossover, as the Standard Model predicts with the measured Higgs mass, then the universe simply cooled and particles acquired mass in a continuous way. But if the transition was a first-order phase change, with bubbles of the new phase forming and expanding, it could have created the right conditions for the matter-antimatter asymmetry we see today. In such a scenario, the walls of these bubbles would have been sites of extreme physics, possibly favoring the survival of matter over antimatter. The Standard Model, with the Higgs mass as measured, predicts a smooth transition, no bubbles, no violent dynamics, and no mechanism for generating the observed excess of matter. This is a problem, because the universe is clearly dominated by matter, not antimatter. To explain this, physicists look to extensions of the Standard Model. Additional Higgs particles, supersymmetric partners, or new scalar fields could alter the shape of the Higgs potential, making the transition more abrupt and providing the necessary conditions for baryogenesis, the process that tipped the balance in favor of matter. CERN's experiments are at the forefront of this search. By measuring the properties of the Higgs boson with increasing precision, scientists hope to find signs of new physics that could have influenced the electroweak phase transition. Deviations in the Higgs self-coupling, exotic decay modes, or the discovery of additional Higgs-like particles would all point to a richer structure underlying the Standard Model. So far, the data matches expectations, but the measurements are not yet precise enough to rule out all possibilities. The high luminosity upgrade and future colliders will push these tests further, probing the very moment when the universe's fundamental symmetries were broken. Another deep mystery lies within the strong nuclear force, which binds quarks together inside protons and neutrons. The theory that describes this force, quantum chromodynamics, allows for a term in its equations that would violate the combined symmetry of charge and parity. If this term were significant, it would give the neutron a measurable electric dipole moment, a tiny separation of positive and negative charge within the particle. Decades of experiments have searched for this effect, but none has been found. The upper limit on the neutron's electric dipole moment is now so small that the CP violating term in QCD must be less than 1 part in 10 billion. This is known as the strong CP problem. There is no reason, within the mathematics of QCD, for this term to be so small. It appears to be fine-tuned, a coincidence that demands explanation. One elegant solution is the introduction of a new symmetry, which would dynamically set the problematic term to 0. This symmetry predicts the existence of a new particle, the axion. Axions would be extremely light and interact only very weakly with ordinary matter, making them difficult to detect. They would have been produced in abundance in the early universe, and could still be present today, forming a cold, diffuse background that might account for dark matter. CERN's ability to search for axions directly is limited, as they are too light and weakly coupled to be produced in high-energy collisions. However, the physics of axions is closely connected to the Higgs and the strong force, and measurements at the LHC help constrain models that predict axion-like particles with different properties. Dedicated experiments elsewhere use strong magnetic fields and sensitive detectors to hunt for axions. But the search is supported by the precision measurements made at CERN. If axions are found, they would solve two major problems at once: the strong CP problem and the mystery of dark matter. The quest to understand the universe's deepest secrets is not limited to the LHC. Around the world, physicists are designing new machines and experiments that take different approaches. In China, plans are underway for a circular electron-positron collider, a ring even larger than the LHC, designed to produce Higgs bosons through electron-positron annihilation and measure their properties with unmatched precision. In Japan, the International Linear Collider has been proposed, which would accelerate electrons and positrons in a straight line, avoiding the energy losses that come with circular machines. The United States is exploring the possibility of a muon collider, which could reach higher energies in a smaller footprint, though the technical challenges are immense. Smaller experiments also play a crucial role. Fixed target experiments smash beams into stationary blocks of material, allowing for the study of rare decays and the search for exotic particles. Neutrino experiments send beams through the Earth, measuring how these elusive particles oscillate between different types. Underground detectors wait in silence for the faint signal of a dark matter particle colliding with a nucleus. Space-based observatories watch for cosmic rays with energies far beyond anything we can produce on Earth, providing a glimpse into natural accelerators powered by supernovae and black holes. The field of particle physics advances on many fronts at once. No single machine or experiment will answer all the questions, but together they map the territory of the unknown. The nightmare scenario for physicists is that the LHC and its successors complete their programs, every analysis is performed, every channel is searched, and nothing new is found. The standard model would stand unchallenged, with no deviations, no anomalies, and no cracks. Some argue that even this outcome would be valuable, forcing a rethinking of the principles that have guided the field for decades. Others believe that the unknown will always remain, just out of reach, waiting for the next leap in technology or understanding. History suggests that surprises are inevitable. After the discovery of the electron, physics seemed nearly complete. Yet relativity and quantum mechanics soon revolutionized the field. After the standard model was completed, new mysteries like dark matter, dark energy, and neutrino oscillations emerged. The deepest discoveries often come when the field appears stuck, and the only way to find them is to keep asking questions, building new machines and exploring the unknown. Imagine the day when a new discovery is made at CERN. It might begin quietly, with a graduate student reviewing routine plots and statistical analyses, just as they have done countless times before. Perhaps they notice a small but persistent bump in a distribution, a subtle excess of events at a particular energy, too sharp to be dismissed as background noise, too significant to be a random fluctuation. The student checks their code, reruns the analysis, and the anomaly remains. They alert their supervisor, who brings it to the attention of the collaboration. Word spreads, but only within the team. Secrecy is essential until the result is confirmed. As more physicists examine the data, independent analyses using different methods confirm the excess. The statistical significance grows 3 sigma, then 4, and finally 5 sigma, the gold standard for discovery in particle physics. Meaning the probability of a fluke is less than 1 in 3 million. A meeting is called, and in a packed auditorium, the results are presented. The room is silent as the evidence is laid out, slide by slide. When the final significance is announced, applause erupts. Some scientists are moved to tears, knowing that years or even decades of work have led to this moment. The discovery is then shared with the world. Press conferences are held, headlines are written, and the new particle or phenomenon is given a name. Theorists scramble to explain it, and the entire field shifts as textbooks are rewritten and new experiments are planned. Sometimes, discoveries confirm what was expected, as with the Higgs boson, which fit neatly into the standard model. Other times, they shatter expectations, as with the discovery of the universe's accelerating expansion, a finding that introduced the concept of dark energy, which no mainstream theory had predicted. The next breakthrough at CERN could take many forms. It might be the long-sought evidence for supersymmetry, confirming the existence of partner particles for every known particle. It could be the discovery of extra dimensions, or a 4th generation of quarks, completing a new pattern in the particle zoo. Or it might be something no one has imagined, a violation of a fundamental symmetry, a breakdown of quantum mechanics at high energies, or a signal from a sector of physics that has yet to be named. The machines at CERN will keep running, the data will keep accumulating, and the analyses will keep improving. One day, the plots will reveal something new, a crack in the standard model, a sign that our understanding is incomplete. The standard model, for all its successes, cannot be the final theory. It does not include gravity, it cannot explain dark matter, and it offers no solution to the matter-antimatter asymmetry. It contains many arbitrary numbers, with no deeper explanation for why they take the values they do. Something more fundamental must exist, and the search for it is the driving force behind every experiment at CERN. The Large Hadron Collider has already recorded hundreds of trillions of collisions, each one a tiny recreation of the universe's first moments. Most of these collisions have been analyzed, but the process is never truly finished. New techniques, such as advanced machine learning, continue to extract more information from old data. Improved calibrations and theoretical insights can change the interpretation of past measurements. Sometimes, the most important discoveries are made not by collecting new data, but by looking at existing data in a new way. CERN is committed to preserving all the data collected by the LHC, ensuring that future generations of physicists can reanalyze it with better tools. Portions of the data have even been released to the public, allowing students, independent researchers, and citizen scientists to join the search for new phenomena. The potential for discovery is enormous. A particle that decays in an unexpected way, a subtle correlation between variables, or a small excess in a distribution could be hiding in the data, waiting for someone to notice. The next major upgrade to the LHC, the high luminosity LHC, will increase the collision rate dramatically, making rare events more common and improving the precision of measurements. The detectors are being rebuilt to handle the increased data rate and radiation levels, with new technologies that can distinguish particles from overlapping collisions and record their arrival times with unprecedented accuracy. Machine learning algorithms will run in real time, filtering the data before it is even recorded, ensuring that no important event is missed. The physics goals for the upgraded collider are ambitious. Scientists hope to measure the Higgs boson self-coupling with enough precision to test the shape of the Higgs potential, observe rare decays with definitive significance, and search for new particles in scenarios that are difficult to probe today. Every component of the machine and its detectors is being improved, involving thousands of engineers and scientists from around the world. The cost is high and the timeline is long, but the potential rewards are immense. If new physics exists just beyond our current reach, the upgraded collider will be the tool to find it. But even as the LHC is upgraded, physicists are looking ahead to the next generation of colliders. The future circular collider, proposed to be 4 times larger than the LHC, would allow for even higher energies and greater precision. It could start as an electron-positron collider, producing Higgs bosons with extraordinary accuracy, and later be upgraded to a hadron collider with collision energies far beyond anything possible today. The technical challenges are immense, and the cost is estimated in the tens of billions of dollars. But the scientific potential is unmatched. Other designs are also being considered, such as a muon collider, which could achieve high energies in a smaller ring, or linear colliders that avoid the energy losses of circular machines. Each approach has its strengths and challenges, and the choice will depend on technological progress, funding, and scientific priorities. What is certain is that humanity will not stop building colliders. The questions are too important, and the mysteries too deep, for the search to end. The ultimate goal is to find the crack in our understanding, the anomaly, the deviation, the unexpected result that points the way to new physics. Every measurement, every analysis, every upgrade brings us closer to that moment. The universe has been hiding its secrets for nearly 14 billion years, but with each collision, each new idea, and each technological advance, we move a little closer to uncovering them. At 4 locations around the 17-mile ring of the Large Hadron Collider, the particle beams cross paths, and it is here that the most advanced scientific instruments ever built stand, ready to capture the aftermath. These detectors are not just large, they are monumental, dwarfing most other scientific apparatuses. Atlas, for example, rises as tall as a 7-story building and stretches nearly half the length of a football field. Weighing more than 7,000 tons, it surpasses the Eiffel Tower in mass. Yet it is designed to measure the tiniest fragments of matter with a precision finer than a human hair. The name ATLAS stands for a toroidal LHC apparatus, referencing the massive toroidal magnets that curve the paths of charged particles as they emerge from the collision point. The detector is constructed in concentric layers, much like an onion. The innermost layer is a tracker, made of silicon sensors arranged in cylinders and disks, which records the trajectories of charged particles with micrometer accuracy. Billions of sensor channels feed data to computers that reconstruct the paths of these particles, allowing physicists to piece together what happened in each collision. Surrounding the tracker is the calorimeter, a device that stops particles and measures their energy. Electrons and photons deposit their energy in the electromagnetic section, while hadrons, particles made of quarks, penetrate deeper into the hadronic section. By the time particles reach the outer edge, almost nothing escapes except muons, which are heavy enough to punch through the calorimeter without stopping. The outermost layer of anomalies is dedicated to detecting these muons, using chambers filled with gas to record the ionization trails they leave behind. The toroidal magnets bend their paths, enabling precise momentum measurements even at the detector's periphery. CMS, the compact muon solenoid, takes a different approach. Though smaller in size, it is even heavier than anomalies, packing 14,000 tons into a cylinder about 50 feet long. The word compact is relative, as CMS is still a giant among scientific instruments. Instead of toroidal magnets, CMS uses a single, powerful superconducting solenoid to generate a magnetic field 100 times stronger than Earth's. This field bends the paths of particles inside the detector, allowing for precise tracking in a more confined space. The two detectors were designed by independent teams, using different technologies and analysis strategies. This redundancy is intentional and crucial. When both anomalies and CMS observe the same signal, the result is almost certainly real. The discovery of the Higgs boson, for instance, required confirmation from both detectors. Each found a bump at 125 billion electron volts, and the probability of both being wrong was vanishingly small. This dual approach is a hallmark of CERN's commitment to scientific rigor. The detectors operate continuously during data taking periods, recording collision after collision, year after year. The harsh environment inside the LHC means that sensors degrade from radiation, components fail, and repairs are a constant necessity. Yet, the machines keep working, maintained and upgraded by teams of dedicated engineers and scientists. These detectors are not just tools, they are monuments to human curiosity, built to explore the deepest questions about the universe. Every collision at the LHC generates a torrent of data, about a megabyte per event. With hundreds of millions of collisions each second, it is impossible to record everything. The data rate would exceed the world's storage capacity in a matter of hours. To manage this, the detectors employ a sophisticated trigger system that makes rapid decisions about which events to keep. The first level of triggers is hardware-based, designed for speed, and looks for high-energy particles or unusual patterns. Only about 1,000 events per second survive this initial filter. Software triggers then analyze these survivors in more detail, reconstructing particle tracks and calculating energies. Events that might contain rare particles or unexpected signatures are kept. The rest are discarded. This process is not without its risks. If the triggers are too narrowly focused on known physics, they might miss something truly new. To guard against this, some bandwidth is reserved for random sampling, saving a fraction of all events, regardless of their apparent significance. The trigger menus are constantly updated as new theoretical ideas emerge and as old searches are completed. Artificial intelligence is playing an increasing role, with neural networks learning to identify anomalies without being told exactly what to look for. Still, the fundamental challenge remains. Most of what happens in the collider is lost forever, and the discoveries we make depend on the choices we make about what to keep. Once the data is recorded, it is distributed to a global network of computing centers, known as the worldwide LHC computing grid. This network spans more than 40 countries and includes over 170 computing centers. The data flows from Geneva to laboratories around the world, where thousands of processors work in parallel to analyze it. The grid operates continuously, with physicists in different time zones taking over as others sleep. Machine learning has revolutionized the analysis process. allowing for the identification of rare events and subtle patterns that would have been impossible to find with traditional methods. The algorithms are constantly improving, and what was state of the art last year may already be obsolete. Behind every algorithm, though, is a human mind. Physicists design the analysis strategies, check the results, and interpret the findings. The grid amplifies human intelligence but does not replace it. Somewhere in the vast sea of data, patterns await discovery, if only the right questions are asked. CERN maintains archives of all the data collected, ensuring that future generations can reanalyze it with better tools. Portions of the data have even been released to the public, inviting students and independent researchers to join the search for new phenomena. The LHC is not just a machine for smashing particles. It is a time machine, a microscope, and a treasure trove of information about the universe's most fundamental secrets. As the collider continues to operate and upgrades increase its capabilities, the chances of finding something truly revolutionary grow. Whether it is a new particle, a deviation from the standard model, or a glimpse of dark matter, the next breakthrough could be hiding in the next collision, or in data already collected, waiting for the right question to be asked. The process of deciding which collisions to keep and which to discard is one of the most critical and challenging tasks at the Large Hadron Collider. With hundreds of millions of collisions happening every second, only a tiny fraction can be recorded for later analysis. The rest are lost forever, their fleeting evidence of the universe's deepest secrets vanishing before any human ever sees them. This is known as the trigger problem, and it shapes the very nature of discovery at CERN. The trigger system works in stages. The first level is made up of custom hardware, circuits designed for speed, that scan the raw detector signals and flag events with high-energy particles, unusual patterns, or missing energy. These flagged events are passed to the next level, where software algorithms running on powerful computer farms analyze them in greater detail. Here, tracks are reconstructed, particle masses are calculated, and events that look like well-understood physics are filtered out. Only those that appear unusual or potentially interesting are kept for permanent storage. But there is a risk in this approach. If the triggers are programmed only to look for what is already expected, then only the expected will be found. Truly novel physics, something that doesn't fit any known pattern, could slip through unnoticed, discarded before anyone has a chance to see it. To guard against this, the trigger menus always include general categories: events with very high energy, events with strange combinations of particles, or events that simply look odd. A small portion of the data is also saved at random, without any selection criteria, just in case something unexpected is happening in the collisions. The trigger menus are not static. They are updated constantly as new theoretical ideas emerge, and as the focus of the experiments shifts. Artificial intelligence is playing an increasingly important role, with neural networks trained to spot anomalies and adapt to new patterns in real time. The next generation of triggers will be smarter and more flexible than ever before. But the fundamental challenge remains. Most of what happens in the collider is never seen, and the discoveries we make depend on the choices made about what to keep. Not all experiments at CERN are focused on the heaviest or most energetic particles. Some are designed to probe the rarest decays and the most subtle effects. The LHCb experiment, for example, specializes in studying particles containing beauty quarks. These quarks are heavy and unstable, traveling only a tiny distance before decaying. But that distance is measurable and leaves a distinctive signature. LHCb is built as a forward spectrometer, optimized to catch particles that fly along the beamline, where beauty quarks tend to go. By measuring how often different decay modes occur, physicists can test the Standard Model with extreme precision. Even the tiniest deviation from the expected rates could reveal the influence of new particles or forces. So far, LHCb has found no clear deviations, but the measurements are more precise than ever. The constraints on new physics are tighter, and whatever lies beyond the Standard Model must be subtle enough to have escaped detection so far. The same is true for strange quarks, which are lighter but still unstable. Their decays probe the weak force in complementary ways, and decades of experiments have built a consistent picture. The Standard Model describes flavor physics, the way quarks change type, with remarkable success, but it does not explain why the mixing parameters have the values they do. A deeper theory would predict these numbers, but for now, they are simply measured. The search for new physics continues on many fronts. Each experiment, each analysis, each upgrade brings us closer to the edge of what is known. The LHC is not just a machine, it is a global collaboration, a testament to human curiosity and ingenuity. The next breakthrough could come from a rare decay, a subtle anomaly, or a pattern hidden in the data. Or it could come from a completely unexpected direction, forcing us to rethink everything we thought we understood about the universe. The story of the universe's earliest moments is also written in the language of phase transitions. In the first trillionth of a second after the Big Bang, all particles were massless, and the electromagnetic and weak nuclear forces were unified. The Higgs field had not yet settled into its lowest energy state. As the universe cooled, the Higgs field rolled from the peak of its potential into a valley, breaking the symmetry and giving particles mass. This event, known as the electroweak phase transition, split the unified force into the separate electromagnetic and weak forces we observe today. The details of this transition matter enormously. If it was a smooth crossover, as the Standard Model predicts, then the universe simply cooled and particles acquired mass in a continuous way. But if it was a violent, first-order phase change, with bubbles of the new phase forming and expanding, it could have created the right conditions for the matter-antimatter asymmetry we see today. The Standard Model, with the measured Higgs mass, predicts a smooth transition, no bubbles, no mechanism for generating the observed excess of matter. To explain this, physicists look to extensions of the Standard Model, additional Higgs particles, supersymmetric partners, or new scalar fields could alter the shape of the Higgs potential, making the transition more abrupt and providing the necessary conditions for baryogenesis. CERN's experiments are at the forefront of this search. By measuring the properties of the Higgs boson with increasing precision, scientists hope to find signs of new physics that could have influenced the electroweak phase transition, deviations in the Higgs self-coupling, exotic decay modes, or the discovery of additional Higgs-like particles would all point to a richer structure underlying the Standard Model. So far, the data matches expectations, but the measurements are not yet precise enough to rule out all possibilities. The high luminosity upgrade and future colliders will push these tests further, probing the very moment when the universe's fundamental symmetries were broken. The LHC is not the only path forward. Around the world, physicists are designing machines that take different approaches. Some are larger, some are smaller, and some use particles that CERN has never collided. In China, plans exist for a circular electron-positron collider, a ring even larger than the LHC, designed to produce Higgs bosons through electron-positron annihilation and measure their properties with unmatched precision. In Japan, The International Linear Collider has been proposed, which would accelerate electrons and positrons in a straight line, avoiding the energy losses that come with circular machines. The United States is exploring the possibility of a muon collider, which could reach higher energies in a smaller footprint, though the technical challenges are immense. Each approach has its strengths and limitations, and the field advances on multiple fronts at once. No single machine will answer all questions, but together they map the territory of the unknown. The next great discovery could come from any direction, and the only way to find it is to keep searching, keep building, and keep asking questions. The possibility that the standard model could remain unbroken, even after decades of searching, is both daunting and fascinating. If the LHC and its successors complete their programs, every analysis is performed, and every possible channel is explored without finding any new physics, the field will face a profound reckoning. The standard model would stand as an incredibly successful, but incomplete description of nature, with no clear path forward. Some physicists argue that even this outcome would be valuable, as it would force a re-examination of the principles that have guided particle physics for generations. The absence of new discoveries at the energy scales accessible to current technology would challenge the idea of naturalness, and might push the community to accept that some features of our universe are simply the way they are, without deeper explanation. Others are less willing to accept this. They point out that the unknown may always remain, just beyond the reach of our most powerful machines. New particles could be heavier than any collider can reach, or new forces might be so weak that they escape detection. The universe may still hold secrets that require entirely new approaches or technologies to uncover. Funding agencies and governments will face difficult decisions about whether to invest in even larger and more expensive machines if the last generation found nothing new. The sociology of science may shift, with young researchers drawn to other fields, and the talent pipeline for particle physics narrowing. Yet, history offers hope. Physics has often seemed complete, only to be appended by unexpected discoveries. After the electron was found, some believed the end of physics was near, but relativity and quantum mechanics soon revolutionized the field. After the standard model was established, new mysteries like dark matter, dark energy, and neutrino oscillations emerged. The deepest breakthroughs often come when the field appears stuck, and the only way to find them is to keep asking questions, building new tools, and exploring the unknown. The process of discovery is rarely straightforward. Imagine the morning when a new anomaly is found. A researcher, perhaps a graduate student, notices a small but persistent deviation in a plot, a bump where none should exist, or an excess of events at a particular energy. They check their work, consult with colleagues, and the anomaly persists. The collaboration investigates, running independent analysis and cross-checks. If the signal survives scrutiny, excitement builds. The statistical significance grows, and soon the result is ready to be shared with the world. The discovery is announced, and the field pivots to understand its implications. Theorists propose explanations, experimentalists design new searches, and the boundaries of knowledge shift. Some discoveries confirm what was expected, like the Higgs boson, which fit neatly into the standard model. Others are completely unexpected, like the accelerating expansion of the universe, which introduced the concept of dark energy. The next breakthrough could be either a long-sought particle, a new symmetry, or something no one has imagined. It might be a subtle deviation in a rare decay, a new force, or evidence for extra dimensions. Or it could be a signal from a hidden sector of physics, pointing to a reality that current theories cannot describe. The machines at CERN and other laboratories will keep running, the data will keep accumulating, and the analyses will keep improving. Each new dataset, each technological advance brings the possibility of discovery. The LHC's high luminosity upgrade will increase the chances of finding rare events, and future colliders will push the energy frontier even further. The search for new physics is a marathon, not a sprint, and patience is as important as ingenuity. The ultimate questions remain: why does the universe exist? Why do the laws of physics take the form they do? Why is there something rather than nothing? The Standard Model describes the particles and forces we observe, but it does not explain why they exist, or why their properties are what they are. Some physicists turn to the idea of a multiverse, where all possible laws are realized somewhere, and we observe the ones compatible with our existence. Others hope for a deeper, more fundamental theory that uniquely determines the laws of nature. So far, no such theory has been found, and the search continues. CERN's role in this quest is to map the boundaries of what is known, to test every prediction, and to search for cracks in our understanding. Every measurement, every analysis, every experiment is a step toward the unknown. The data collected today may contain the seeds of tomorrow's discoveries, waiting for someone to ask the right question or develop the right tool. The preservation of data, the openness to new ideas, and the willingness to challenge assumptions are all essential to progress. The future of particle physics is uncertain, but the drive to understand the universe is as strong as ever. Whether the next breakthrough comes from a new particle, a rare decay, a subtle symmetry violation, or a completely unexpected direction, it will reshape our understanding of reality. The search for the fundamental laws of nature is a journey without a final destination, always pushing the limits of knowledge and technology. As the LHC continues to operate and new machines are planned, the possibility of discovery remains alive. The universe has kept its secrets for nearly 14 billion years, but with each collision, each new idea, and each technological advance, we move closer to uncovering them. The next crack in our understanding could appear at any moment, and when it does, it will open the door to a new era of physics. The story of the Large Hadron Collider is not just about machines and measurements. It is about human curiosity, collaboration, and the relentless pursuit of knowledge. It is a testament to what can be achieved when people from around the world unite to explore the unknown. The search will continue, and when the next discovery comes, whether expected or astonishing, it will remind us that the universe is always more mysterious and more wonderful than we can imagine.